Okay, hi guys. I'm sorry it became a little late. There is some connection issue, there is some link problems, and so on and so forth. So yeah, I hope everybody's doing good, right? I see how many? I see almost 13 people are there. If I am made,
good evening, sir.
Good evening, good evening. I have to be made the host. 1 second, then I can share my screen. Yeah, okay, I think it's fine now. Right, so let's start. Let's quickly start. Let me share my screen. I hope everybody is able to see the screen. Okay, so I think this was the exact page we require. We'll just look into what and all we saw actually for so many things last class. We'll just see what are those things. Okay, so we started with this emission spectrum of hydrogen, right? So it all started with this transition energy formula. Transition energy delta E is equal to RH squared into 1 by, we write it as Ni, so it's here, right? So we write it as 1 by Ni squared minus 1 by Ns squared, initial to final, right? But that can be for both absorption or emission for that matter. But if you're talking about emission, that is when the electron comes from higher level to the lower level, right? Then we write N1 and N2, that is N1 squared and N2 squared. Here, N1 and N2 represents the lower orbit, I mean, where the electron comes here, right? The lower orbit and the higher orbit. Obviously, the transition is always going to be, for in this case, the transition is going to be between higher level to lower level. N1 is lower, N2 is higher, right? And then hope you all remember how this RH came. I basically had delta E is equal to some Z squared into 1 by N1 and 2 squared. But I had this, the E is equal to HC by lambda. So if I write the HC and K, all these will come together to become the Rydberg constant. We know the value also, right? Okay, so I told you, depending on this N1, where the electron comes, where the electron goes at last, whether it's the first level or second level, it can come from any other level. Higher level, it can be 5, 6, 7, 8, 9, 10, whatever be the level. But depending on this N1, that is the lower orbit, where the electron at last goes, based on that, we have different series, right? So first starting with something called as Lyman series. Lyman series, I told you the N1 is always 1. Wherever the electron starts from, it is always it is going to end up in the first level. You can see the diagram here, right? Wherever the electron starts from, it is going to end with N1. That is, I mean, N is equal to 1, right? And then, so you can see here, the N1 is always 1. N2 can be anything, right? And it falls into the spectrum of UV. Okay, like the radiation which you're going to get, because electron comes from higher level to the lower level, you are going to see radiations, and those radiations are going to be in the form of UV radiations, right? So like that, we have Balmer, Paschen, Brackett, and Pfund. Now you just have to go on consecutively increasing the N1 value. So for Balmer, N1 is equal to 2, for Paschen it's 3, for Brackett it's 4, for Pfund it's 5, right? And again, N2 can be the next, anything higher than this, anything higher than N1, right? And then if you look at what kind of radiations you're going to get, we already saw for Lyman, it is UV. For Balmer, it is visible. And for all the other three, it is infrared radiations, right? I hope you all know UV is ultraviolet. Okay, fine. Anyways, then we went on to see there can be questions like asking you, find the largest lambda in a particular series. It can be Lyman, Balmer, Brackett, Pfund, it can be anything, right? So obviously all the other things are constant, right? If you look at this formula, right? RH is a constant. Z will be a constant depending on the what kind of element you're speaking about. The only variables are N1 and N2. And that too, if you fix what is the series, whether it's Lyman or Balmer or Paschen, N1 is also fixed, right? So N2 is the only variable in these kind of questions. Okay, so how do you remember this? Like I gave you the logic also. Anyways, you can remember it like this. So for largest lambda, right? For lambda is equal to maximum, N2 should be, right? Oh, it's here. I'm sorry. We'll start, I think, with this. Yeah, sorry. For lambda max, that is for maximum value of wavelength. Obviously, you can look at the formula E is equal to hc by lambda. So E and lambda are inversely related. You can see here, right? You can see E and lambda are inversely related, right? So highest lambda means minimum value of energy. So anyways, for that, you have to understand that the N2 value should be the next value for N1. That is N2 is equal to N1 plus 1, right? Okay. Same way for lambda minimum or energy maximum, and N2 should be infinity, right? Now, either you can remember it like this, if you want to by heart, you can by heart, or you can always remember the logic, how it's going to be, right? Say, if I talk in terms of energy, if I look at these are what are called as energy level diagrams. Okay, anyways, so say we talk about N is equal to 1 Lyman series, right? Now you understand that, say, if the electron comes from second to the first level, right? Second to the first level, what will you see is energy will be minimum because it's the lowest, like say very small distance, right? So energy will be minimum. So lambda will be maximum. For that only we say for lambda max, N2 is equal to N1 plus 1. Like the consecutive, the next alternate energy levels, if the transition is going to happen, that is where I have minimum energy and that is where I'll have maximum lambda. Right? And for maximum case, obviously now I want maximum energy, right? For maximum energy, obviously electron should ideally speaking, should come from infinity to whatever the lowest level is, right? So obviously then only I'll have the highest amount of energy and lambda minimum, and that's why we keep N2 as infinity. Hope you all remember this, right? Okay. And then what we saw, yeah, we did some problems, all this, right? And then yeah, okay, this is okay. Fine. And then this is where we ended up with what are the drawbacks of Bohr's atomic model. The first drawback we already know that it is going to work only for single electron species, right? For say hydrogen, helium plus, lithium 2 plus, beryllium 3 plus, only for these kind of species it will work, right? And it does not explain Stark effect and Zeeman effect. We told you what is Stark effect and Zeeman effect. Stark effect is if I have one particular spectral line, say one line, this particular line I take, and if I'm going to apply some electric field, right? Now this line will split into different, like say so many number of lines. So this splitting of spectral lines in the presence of electric field is what is called a Stark effect. And if the same thing happens in the presence of magnetic field, then it is going to be called a Zeeman effect. Same splitting of spectral lines in the presence of magnetic field is what is called as Zeeman effect. So this was not, this property was not able to be explained by Bohr, right? Next comes obviously Bohr Bohr considered electrons to be only particles, right? But when de Broglie's hypothesis came into the picture, yes, any questions? Anybody has any questions? Okay, fine. So anyways, so Niels Bohr took only electron to be particles, right? He considered only electron to be particles, but we know that electrons are going to consider, they are going to have both particle as well as wave nature, right? So that was coined by this scientist named as de Broglie, right? So you know what he said? He said that the world is symmetrical, and so is light or electron, right? Everything has two sides, right? Head, tail, life, death, like always two things, night, day. So like that, everything will have two properties. So like that, so he said the light will also have two properties in the sense that they will have both particle nature as well as wave nature. As same goes with electrons. Okay, then he combined the two famous equations, one given by Einstein, another given by Planck, E is equal to hc by lambda, right? Then he combined these two, and this is what we end up with. Lambda is equal to h by mv, right? And this lambda is what is called as de Broglie's wavelength. Okay, very important formula. Lambda is equal to h by mv. Okay, and this mv can again be written as p. P is momentum, right? We know momentum is equal to mass and velocity, right? Okay, then other problems where this again, the famous one, Heisenberg's uncertainty principle. We saw the scatter the box experiment, right? So unless and until we open the box, we really don't know whether the cat will be dead or alive, right? So till that time you open and check it, right? The cat is always going to be in a state where it is both dead as well as alive. Complicated, right? Anyways, so if at all I have to talk in like more scientifically, right? So what he said, right? What Heisenberg said is that no two conjugate quantities can be measured with 100% accuracy if you measure it simultaneously. At the same time, you try to measure two conjugate quantities. Conjugate means opposite quantities, right? So if you try to do that, you are always going to have some error, right? And in physics, right, we have two sets of conjugate quantities. One is position and momentum, another is energy and time, right? Okay, so now if you look at your Bohr, what he did, he calculated the radius. We know the formula for radius according to Bohr's theory. We know what is the momentum's formula also, right? So Rn describes the position, MVR, that is the angular momentum, describes the momentum, right? So both these things can be calculated simultaneously if, I mean, according to Bohr, right? But Heisenberg said that it is not possible, right? So now, obviously, he said that obviously there's going to be some error, right? So if I take the errors, if we multiply the errors in position and multiply it with the error at momentum, or you can also call it as uncertainty, right? Uncertainty in position or uncertainty in momentum. If you just multiply them both, they'll always have some minimum value. So this error is always greater than or equal to h by 4 pi. Again, a very important formula, right? And I told you we can modify this a little bit because I know position, I mean, momentum is m into v, mass is a constant, so I can write m out of this delta. There will not be obviously any error in mass, right? So this way also you can rewrite this equation. Now, same thing can be done for your energy and time also. Delta E into delta T is always greater than or equal to h by 4 pi. Okay, so now what we're going to do is that we will do some problems on de Broglie's wavelength. Okay, and then we'll do some problems on Heisenberg's uncertainty principle. Okay, and then we'll go on to see this photoelectric effect. What is this? I told you that electron has both particle as well as wave nature, right? Now, this particular thing, the photoelectric effect, proves that it is going to have what is it? Particle nature. Photoelectric proves that it is going to have particle nature. Okay, right? So we'll see what is going to happen. We'll try to do some problems before that. Please take note of the questions. Anybody has any questions? Because we saw so many things last class. If you have any questions, please feel free to ask.
Can you explain about de Broglie thing?
Yeah, de Broglie wavelength. Sure. So what happened is, so like you understood what de Broglie said, right? The hypothesis you understood. Basically, everything is symmetrical, and so basically light will have both particle nature as well as wave nature. That is okay.
That everything is symmetrical.
Everything is symmetrical means, like, say, entire world is symmetrical. Symmetrical means it can be cut into two halves. That is what is being symmetrical. Means, like, say, like we can have day, night, life, death, men, women, good, bad, right? So all these are symmetrical. All these entire world is consisting of one half and the other half. That's what he said. So obviously, if everything is like that, why not light? That's what he said. Yes, okay. Understood? Right? And obviously, the equations are very simple. E is equal to, you just connect these two equations, and you get the equation for lambda. Lambda is equal to h by mv. The C becomes V. That this C is only for light, since you talked about light, but V is for any thing which is having any velocity for that matter. That's the thing. So this is what you have to remember. Lambda is equal to h by m. Okay. Right. Any other questions anybody has? Anybody wants to repeat? Yeah, please tell me.
So can you once again just tell the statement of Heisenberg uncertainty?
Yeah, sure. You want to take it down? You want me to tell it slowly?
Yeah,
okay, sure. So the statement goes like this. If anybody else also wants to take down, please take down. Anybody has missed it. Okay. So no two conjugate quantities can be measured. No two conjugate quantities can be measured simultaneously. No two conjugate quantities can be measured simultaneously with 100% accuracy. With 100% accuracy. So the entire statement goes like this. No two conjugate quantities can be measured simultaneously with 100% accuracy. Right? So if there are two conjugate quantities, it is not possible for us to measure them simultaneously without any error. That's what it means. Okay?
Yes, I got it.
Right. Anybody else? Anybody question? Any other questions from previous class or from previous chapter? Anything? Anybody has any concerns? Okay, fine. If that's If that's the case, we'll move on. We'll move on to today's class. Okay. So okay, take the question. Find the wavelength. Find the wavelength in nanometers. Find the wavelength in nanometers for a proton. For a proton of mass. For a proton of mass So what happened? This thing is not working for me. One second, people. Why my cursor is not moving? What happened? Okay, give me a moment. Just a moment. There's a problem here. 1 second. Okay, I'm so sorry, guys. Like whatever the pad on which I write, but there was a technical problem. Okay, half an hour got wasted. So, anyways, so I was telling that question, right? So the question is: find the wavelength of a proton of mass 1.67 into 10 to the power minus 27 kgs. Okay, find the wavelength associated with a proton of mass 1.67 10 to the power minus 27 kgs, moving with a velocity, moving with a velocity of 10 to the power minus 3 meter per second. Okay, moving with a velocity of 10 to the power minus 3 meter per second. Okay, right. Go on. Which formula you have to use, people? Which formula you have to use? Here, look at the question. They're asking you find the wavelength.
The lambda equals h upon
mv, right? So de Broglie's wavelength is what you have to find, right? So they are given the mass, m value is given, v value is given, right? You know the h value. H value, anybody wants to tell me? H value is what?
6.6 into 10 to the power minus 34.
Yeah, 6.6 into 10 to the power minus 34, right? So all these values are there. Just substitute in the formula and tell me the answer, quick. And I want the answer in nanometers, wavelength in nanometers.
So 1 meter is equal to 10 to the power minus
9 meters. 1 nanometer. 1 nanometer is 10 to the power minus 9 meters.
So this is 3.95 into 10 to the power minus 13.
Nanometers.
Yes, sir.
3.95. 3.9. See, okay. How are you getting 10 power minus something in nanometers? If you check, say lambda is equal to h by mv, right? So h is 6.6 into 10 to the power.
So 3.95 into 10 to the power minus 22.
Meters. Like in nanometers, are you getting these answers? I don't know what's wrong. Okay, we'll check. So this is m is 1.67 into 10 to the power minus 27. And v, they have given it as 10 to the power minus 3. Right? So I have 10. This alone will give me 10 to the power minus 30. So above I have 10 to the power minus 34. So I can cancel this entire thing and write 10 to the power minus 4 here. No problem. Okay. Right? Because 34 and 30 anyways will become 10 to
So
the
sorry,
minus
sir.
34.
3.95 into 10 to the power 5.
10 to the power 5 nanometers.
Yes, sir.
Okay, fine. So this value, what I want to know in the phone, I want to know what is this value? 6.6 into 6.6 divided by 1.
It's 3.95.
It's 3.95.
Yes.
Okay. So where is it? Okay, 3.95 into 10 to the power minus 4 meters is what you're getting, right? So if I write it in nanometers, what I should do? I should actually multiply
Divide by 10 to the power
divide by 10 to the power minus 9, right? Oh, then you'll become, no answers are matching. Why? One in 10 to the power minus 3 meter per second, H is okay, kg, everything is in proper units. So this many meters. So I should obviously divide it by 10 to the power. All right. I should divide it. Okay, fine. I should divide it. Then it will become 3.95 and 10 to the power 4. Okay, fine. I think the book answer is wrong. Maybe what you're getting is only like nanometers. Okay, right?
So 10 to the power 5.
10 to the power 5. Yes, this is 10 to the power 5. Yeah. Okay. Right. Maybe the book answer is wrong.
Sir, can you explain the units of these things?
So here, this one, right? The H value
H
will
is
be
joule per second, sir.
Joule second, right? Because
Sorry,
E is equal to H nu, right? So this is per second, joule per second. No, that's what this will come down. So H is basically E by nu, right? So this will be joule by per second. Now this per second goes up, right? It will become joule per second. It's like, see, it's like 1 power 1 by 1 power 1 minus 1 or 2
Yes,
power, it's like that. So anyways, this is joule second, right? Joule second, and then this would be meter per second, and M value will be in kg, right? So there is a connection between kg and joules. That's all you have to know. The kg and joules, if you want to have understanding, right? E is equal to half mv square. Right, now this will be in joules, so you'll get a connection between joules and kg. Right, so anyways, all the units are perfectly matched here. You don't have to worry about the units. If you just substitute the SI units for all of them, everything will be taken care.
Sure, but there is an extra S, right?
Extra S. That's what. Like if you check, this will be extra second is there. Here also I have a second, right? In meter per second.
Sure, but no, in the numerator there are 2 seconds, but in the denominator only 1 second, sir.
In the numerator I have joule second. Okay, see if I write it properly. In the numerator I have joule second, and I have kg, and I have meter per second.
Yes, sir.
Correct. Okay. Then if it is it. Yeah, the units are a problem. Maybe I'll look into this. Like how, basically it will be taken care, because you see that for velocity, again, like basically if I write E is equal to half mv squared, right? Now this is joules, and you have for M is kg, and for this again you have meter per second. So you actually have a connection between
meter square second minus 2, sir.
Okay, meter square. So whatever. All I'm trying to say here is that here you're getting a second and all, so everything will be cancelled. All will be remaining is only this meter. Okay, and that too it will be the numerator. That's what you'll be getting. Don't worry. Like, you don't have to worry about the units, man. It will be fine. It is going to be completely all right. If you are really interested into this, all you have to do is my dimension analysis. Right, in your first chapter, you do.
No, sir. Over here, the kg and kg gets cancelled. Meter gets cancelled, and 1 meter is left in the numerator, as that is what we need. And but there are over here it's s to the power minus 2 in the numerator, and in the bottom it's h to the power minus 1. So 1s should be remaining, right?
1s should be remaining.
Oh no, sir. Sorry, it's joule second. So it
yeah, exactly. Joule second. Correct. That's what it will be correctly coming out. Not a worry at all. You don't have to worry about the units. Okay. Right. Fine. So this is our question.
Can you repeat the last question?
Can I repeat? You want to repeat the question?
Yes, sir.
So find the wavelength in nanometers for a proton of mass 1.67 10 to the power minus 27 kgs, moving with a velocity of 10 to the power minus 3 meter per second. Okay.
Sir, how can velocity be 10 to the power minus 3, sir?
How can velocity be 10 to the power minus 3?
Yes, sir.
Why cannot it be? It is a 0.0. I mean, 10 power minus 3 is what basically 0.001 meter per second. That's what it means. Is it not? This is also a number, right? 0.001.
Yes, sir.
Okay, right. Are you satisfied with my answer? Did you understand?
So, like, does that road the velocity such a low velocity?
Sorry.
That's a very small velocity.
Maybe it's just a question, man. Right? It doesn't, like, logically. If you think, yeah, obviously proton will move a little more faster. Obviously,
no, but sorry, sir, but proton doesn't revolve, right?
Oh no, man! It is just a hypothesis. If at all it is moving like this, Obviously, proton movement can be there. Alpha rays or what? Alpha rays are basically positively charged, right? Say if I have H plus ion moves inside the solution. What does contain? Contains only a proton. Are you able to understand? Right. So, anyways, like if you think into the logical aspect of every question, actually, you might not be getting the logical aspects every time. But this question do have a logical aspect, right? This velocity is possible, right? And then if you talk about how protons are moving, yes, H plus ion is nothing but a proton. So it moves. Conducts electricity or not. So obviously it moves. Okay. Right. Right. So next question. Move. Start with some easy question. Okay, take down. The uncertainties in measurements of position. The uncertainties in the measurements of position and momentum. The uncertainties in measurements of position momentum are equal, comma, are equal, then put a comma. Actually start the question with like, if the uncertainty in the measurement, like that you start. So the question is, if the uncertainty in measurement of position and momentum are equal, comma, calculate the uncertainty in velocity. Calculate the uncertainty in velocity of a particle. Calculate the uncertainty in velocity of a particle of mass 1.21 into 10 to the power minus 18 kgs. Okay. Of mass 1.21 into 10 to the power minus 18 kg. So I'll repeat the question, people. If the uncertainty in measurements of position and momentum are equal, calculate the uncertainty in velocity of a particle of mass 1.21 into 10 to the power minus 18 kgs. Okay, think about this. We'll answer it again. I'll try to answer the question again. Perfect. You try.
Sir?
Yeah. Tell me. Someone has a doubt? Oh, I'm not on mute. Am I? No, right? Any problem?
Sir, could you hear me?
Yeah, I'm able to hear you now. Yeah, please tell me.
1 minute, I'm not able to hear you.
Guys, everybody able to hear me, or only he's not able to hear?
You're audible, sir.
Okay, fine. Then
yes, sir, audible now, sir. Sir, okay. Can you repeat the question once again?
Yeah, sure. So the question is, if the uncertainty in measurements of position and momentum are equal, comma, calculate the uncertainty in velocity of a particle of mass 1.21 into 10 to the power minus 18 kgs. So question. Okay, hope you all know which formula to use. It's Heisenberg's uncertainty principle. So all I have is delta x into delta p is greater than or equal to h by 4 pi. You don't have to worry about greater and simple. You can use equal to. Okay, and you can use directly, or for not only for this question, for any question, you can directly use equal to. Okay, and delta x, this delta p, I know how to write, right? M into
delta u.
Delta v is equal to h by 4 pi. This is the exact formula which you have to use.
Sir, 1 by 2m into whole root of h by pi.
Oh, you're getting quadratic equations and all?
No, sir, not quadratic equation.
What is the answer?
So, I'll first tell the whole root term. Whole root of h by pi.
H by pi.
Into half m.
Into half times?
M, mass.
Okay, whatever be the mass. Okay. Fine. The mass is given to you, right?
Sir, 4.34 into 10 to the power minus 14.
4.34 into 10 to the power minus 14. That is uncertainty velocity. The answer.
Yes, sir.
Okay, let me check. So basically, you must be getting the delta V as 1 by 2m into root of h by pi. Is it right? This is what you should be getting. This is what you told here, correct?
Yes,
Someone
sir.
told that. Okay, so 1 by 2m into root of h by pi. So yeah, this calculation is very difficult on this side. I understand. 1 by 2 into 1.27 into 10 to the power how much? What is the mass value given? 18. Right? Into root of h value is 6.68 10 to the power minus 34 divided by your pi value is how much? Is it 3.1? Okay. Right. So yeah, it's a very big calculation, people. Right. You don't have to do it now. You don't have to waste time. So the answer approximately what you will be getting is 6 meter per second. Right. You have to mention the unit also. We're talking about velocity. Even though talking about uncertainty in velocity, you have to use the unit. Right. For x, that is for delta x, you'll use meters. For delta v, I'll use meter per second. Don't remember this. If you don't put the unit, half mark will be cut. Okay. Right. And if you're wondering how I got this particular equation, it's very simple, people. Right. So now this is what is the equation we have to use. Like delta x into m into delta v is equal to h by 4 pi. Right. Now what they are telling delta x and delta v are same. That's why look at the question. If the uncertainty in measurements of position and momentum are equal, I'm sorry, not delta v, m into delta v. Right. I'm sorry. Yeah, m into delta v. Right. So uncertainty in position and uncertainty in momentum. This entire term p, delta p. Right. So that they're telling is equal. Right. So now how can I rewrite the equation then? Can I rewrite the equation like this? Delta x. Since both are same, I will write this delta x also as delta p. Okay. Right. So what will happen? I'll be basically getting delta p squared will be great, or I can just directly put equal to divided by h by 4 pi. Now what is p? We know is m squared into delta v squared. We can write it like this, right? M is again, we took m out of the delta because it is constant. So it will be m squared into delta v squared is equal to h by 4 pi. Right. Now all we need is only delta v. Right. So delta v squared, I can write it as h by 4 pi into 1 by m squared, right? So now if I take root on both sides, because I don't want this square, if I take root on both sides, you will be ending up with this. You can see here, right? Or if I write it properly, you can write delta V is equal to, now h and pi will be in root, and root of 4 will become 2. So I will write, and this root of here will become 1 by m. So I'll be writing 1 by 2m. This 2 comes from 4, right? And this m comes from root of m squared, right? And what is remaining? Root of h and pi, right? Root of h by pi. So this is exactly what we got. And all you have to substitute the values, m values given, h value, pi value, So approximately, if you substitute everything, you'll be getting the answer as 6 meter per second. That's what you'll be getting.
Sir, I have a doubt, sir.
Yeah.
Sir, I did it in a little different method, but I think I did not get the same answer.
Okay, but I think I checked the calculation. That's fine. Like if you can get this particular equation, this delta V is equal to 1 by 2, root of h by pi. That if you get, you are going to get the answer.
Sir, no, what I did was I wrote delta x in terms of delta V.
Okay.
Sir, so delta x equals mass times delta V.
Delta x equals mass. Okay, delta. Okay, fine.
And then, so mass times delta V square equals h upon 4 pi.
Mass times delta V squared. Correct, exactly. But it will be mass squared into delta V squared, not only mass into delta V squared, right? It is mass square should come. You're writing delta P squared, basically delta X into delta V is what is h by 4 pi, right? So it should be, if I make these both equal, it becomes delta P squared, which will become m squared V squared. Generally, if it's just P squared. Now, since we have delta P squared, it is m squared into delta V squared. That's the only difference.
Yes, sir.
Okay.
Yeah.
There only made a mistake. Okay. Cool. No issues. No issues. Okay. I hope everybody understood what we did here. Okay. They're telling uncertainty in position, uncertainty in momentum, both are same. Right. So either of this can be written again as delta P. Right. So we did that. Yes. Please tell me.
So can you once write Heisenberg uncertainty principle formula?
Okay. I'll write. Right. It would be delta X into delta P is greater than or equal to h by 4 pi. This is the formula.
Yes, sir. Then why are we considering or equating here? It could also be greater, right?
Oh, okay. Actually, the question in the question they must specify, find the minimum uncertainty. They should specify this actually in the question. Okay, what you're asking is absolutely right. Right? The minimum value. If I want to find minimum value, this greater than or equal to will become equal to. Understood?
Yes, sir. Got it.
Right? Then, like, even though they don't tell you anything about the question in the minimum and all, they don't mention, still you use it only equal to sign. Okay, don't worry about the greater than sign. Right?
Fine, sir.
Okay, cool. Fine. I hope everything is clear for everybody. Right? So maybe, I think enough, right? It is the two formulas. I think de Broglie's real in one question and your Heisenberg's uncertainty principle one question should be enough. Very small formulas. You have to substitute, but the calculations would be a little difficult here because h is there, like pi is there, all these things are there. So calculations might become difficult, but the formulas are very, very simple. Very, very simple. Okay, right? Fine. I think we'll move on today. Okay, so we'll move on to see this important thing called as photoelectric effect. So now, guys, this is a very, very important phenomena, and this was again discovered or made into effect by Einstein. Okay, fine. So what he did is, or what he observed is that, say he had a metal surface. This is a metal surface. Okay, fine. Now what he did to this metal surface is he illuminated, or he made sure light falls on this. Okay, he made sure light, some light, right? Any visible light, red light or orange light, something, right? He made this light made to be fall on the metal surface. It fell on the metal surface, right? Now what he observed right? What he observed when the light hits the metal surface is that from the metal surface, electrons are ejecting out, right? So electrons are ejecting out. This is a very, very simple thing. Okay, there is a metal surface, right? To the metal surface, light is illuminated, right? After the light is illuminated, then electron comes out. So electron comes from the metal comes out. That is what he observed. Okay, now this entire effect is what is called as photoelectric effect.
Sir?
Right? Yeah, please tell me.
So basically, reflection will occur, right?
No. It's not reflection. I'll tell you what exactly happens. See, this light will contain some energy. Right? This light will contain, because we know, just now we proved, but if you consider how light will have energy is the question, right? So he said light is made up of certain particles called as photons. Okay, what he said is light is, he didn't consider as a wave. Like I told you, this particular thing proves that light has particle nature. Okay, light has particle nature. That's what is important. Okay, but again, certain people will tell that this photoelectric effect also tells me that it is also can be wave nature also, right? But still, overall, this effect is very important. Whether it's proving that light has particle nature or wave nature doesn't matter, right? But all you have to understand is the effect, because questions can come and it's very pretty interesting. Like if you look at the applications of this, how we are using this photoelectric effect now is enormous. Let me concentrate on this. Okay, so he said light is made up of some particles called as photons. Okay, so if someone asks you a question, what is light made up of? Light is made up of photons. Very simple. Photons are similar to electrons, but they are capable of giving light. It's something like that. Anyways, so light is made up of photons, and these are particles. Okay, fine. So basically, this light will have some energy. Okay, now when this light falls onto the metal surface, what will happen is, say, assume that this is the metal. Now I'm just giving you a cross-section view. Assume that inside the metal there are electrons, right? Obviously, right? And you can understand that metals easily lose electrons, right? Metals easily lose electrons, and non-metal easily accept electrons. Anyways, now you know that there is something called as ionization energy. Is it not? Right? There is something called as ionization energy. What do you mean by ionization energy? Energy required to take this electron out. So not, I want to take this electron out. Obviously, this electron and the nucleus will have some attractive force. So you have to spend some energy to the atom so that this electron comes out. Okay, now the energy you spend in taking this electron out is what is called as ionization energy. Yes, I think till now it's fine, right? So I have to take out the electron, right? Some energy has to be spent, and that energy is what is called as ionization energy. Okay, now this ionization energy is provided by the energy possessed by the light. Okay, this light I told you is going to have some energy, right? Now that energy is more than the ionization energy of this particular metal. Say for example, it can be sodium or cesium, right? Now they generally have low ionization energy. It is very easy for them to lose electron, even if very less amount of energy is given, right? Sodium, cesium, rubidium and all will easily lose electron, very less ionization energy. Okay, so the light which you are using, right? Light which you are using will have some energy that will be more than the ionization energy of this metal. And obviously what will happen? Energy is spent, electron comes out, because the spent energy is more than the ionization energy. Yes, it's not reflection here, right? The light has some energy, it is spent on the metal surface, and the ionization energy is given to the atom, electron comes out. Okay, right? Everybody
sir?
Yeah.
So this is only for the top layer metals. I mean,
not like that. But we will take a very thin metal surface, very, very thin metal surface. I mean, metal, I would say a metal strip kind of stuff, very thin. I will say gold foil, right? Thin gold foil, something like that. Very thin piece of metal we'll take, very small metal.
Okay, sir.
Right. Even if you take the entire bulk, even if you want to take the entire bulk, the electrons which are at the surface, near the surface, are little, less bound to the nucleus, in the sense that you're going to be easily coming out, rather than an electron which is inside the bulk here and all. It is little difficult. because they'll be very strongly attracted towards the nucleus, right? But on the surface, right, they'll be a little far away, so it is easy for me to remove the electrons. That's what you have to understand. Okay, so I hope everybody understood what exactly is photoelectric effect, right? I have a metal surface, light is illuminated, and because of the ionization energy spent, electron comes out. Very, very simple. Yes, any questions anybody want to ask?
Sir, how were the electrons detected?
How are the electrons detected? Okay. These are nothing but cathode rays, right? So something like cathode rays. Again, you can have ZNS3. Scintillations will happen, like how you did in cathode ray experiment. J. Thomson. This is just one of the ways. There are millions of ways to detect electron distance. There are so many ways to do it. One of the ways is using ZNS3. Okay, right? Fine. Now going into, so we understood the effect. We understood the qualification, in the sense that we understood the logic behind it. We understood the science behind it. We understood the logic explanation behind it. That and all we did, right? But obviously we have to speak in terms of numbers, right? To give some mathematics. How will you calculate? Say now this electron is coming out, right? If I want to see how much energy this electron possesses, right? Obviously these electrons are moving, right? These electrons will be moving. So they will have some kinetic energy. Right? These electrons will have some kinetic energy when they are moving. So can I calculate the kinetic energy? And say, what will you understand is that, say, assume that, okay, say that you use light of energy 1 joule. Okay, it started with light of 1 joule and there was no photoelectric effect happening. Say you went to 2 joules, photoelectric effect was not happening. Right? You went to 5 joules, photoelectric effect was not happening. But say if you went to 10 joules, yes, right? After 10, for 9 also it was not happening. I'm just giving you random numbers, people. Okay, right? If I use 10 joules of energy, then I found that the electrons were coming out. And obviously after 10, 11, 12, and all, obviously electron is going to come out. Okay, so yeah, tell me.
So the photoelectric effect is only for metals?
Yeah, obviously this will happen only for metal, and that too for very few metals, sodium, cesium, rubidium. Basically the condition is that you should have very low ionization energy. Like it means the element should be able to easily lose electron. That's the point.
So then if we take suppose a metal such as magnesium and supply more energy to it, then would it happen?
Possible. Instead of light, right? Instead of light, normal visible light, say you go for gamma rays, then possible. Right? What you have to understand is, say compared to magnesium, say, and sodium, magnesium will have higher ionization energy. Right? So obviously, as you said, more energy should be spent. Right? But that energy cannot come from light, visible light, because it has little lesser energy. So if at all you have to use more, you need more energy, you need to go for different radiation itself. Like instead of light, you go for, say, X-ray you use here, right? Or you use gamma rays, or you use UV light. Right? Those and all has more energy than visible light. Those you can use.
Sir, how are you saying that gamma rays has more energy than light rays?
I told you, this is a thing called a spectrum, right? Say you start with, basically it is denoted the order of, say, lower energy to higher energy. Right? Or like we don't have to even go through that. See, you know, gamma rays are very bad for health. Why is it bad for health? Tell me. Because it can penetrate your skin. Gamma rays are so strong that they can penetrate your skin. Same goes with X-rays, right? Say X-rays penetrate your skin, and that is why your bones are visible. Hope you understand. But can normal light do this? Visible light, we are surrounded by visible light everywhere. Does it affect your skin? Because it doesn't have any penetrating effect. It's because its energy is very less. Okay, if the energy is less, it will not be able to penetrate. Since gamma rays and X-rays have more energy, they were able to penetrate. That's how we say that they are going to have more.
Sir, but if we increase the intensity of light rays, would it happen?
Exactly. I was actually coming to that, but what you have to understand is energy and intensity are not related. Okay, let me tell you what exactly intensity is, but give me some time. Right now itself I'll tell. I'll finish this part and come to this intensity part. But now what you have to understand is intensity and energy are not related. Okay, if you increase intensity, energy is not going to be different. I'll tell you how also. Don't worry. We'll come to this point again. Okay, but if at all you need more energy, you have to change the radiation itself. Instead of light, use some other wave. That's what you have to do. Right. Okay. So what I was telling is, where is 1, 2, 3? Okay. So I started with 1 joule. There were the electrons were not coming out. 2 was not coming out. 5 not coming out. 9 not coming out. But when I used 10 joules of energy, I saw photoelectric effects happening. Photoelectric effect happening means what? Electrons are coming out. Okay. Now, till this point, photoelectric was not happening. Photoelectric effect was not happening. But from this 10 joules, photoelectric effect is happening. Okay. So what you have to understand is there should be some minimum energy possessed. Possessed by who? Possessed by the light. Right? The incoming light, the light radiation you use here, right? Right? This should have some minimum energy. Okay? And that minimum energy only if the, say I write it like this. There should be some minimum energy. Right? So for photoelectric effect to happen, right? For photoelectric effect to happen, right? So we understood that there should be some minimum energy possessed by the light radiation, right? So the energy possessed should be greater. Energy of light, okay? The energy of the light which you are using should be greater than this minimum value of energy. In this case, we found that the minimum value of energy is 10 joules. Okay, now instead of using this term minimum energy, we use some technical term which is called threshold energy. Okay, so the energy of light which you are using should be greater than the threshold energy of that particular metal. Okay, obviously different. If I use sodium, maybe it is 10 joules. If I use cesium, it might be say 5 joules. If I use rubidium, it may be say 2 joules, right? So this threshold energy which I'm talking about, the minimum energy, actually what you do is, you write threshold energy and I'm going to give you the definition. Okay, take down the definition for threshold energy. Okay, that makes more sense. Take down. It is the minimum energy. It is the minimum energy which should be possessed. Which should be possessed by the incoming light radiation. By the incoming light radiation. In order for photoelectric effect, in order for photoelectric effect to happen, in order for photoelectric effect to happen, right? So I'll repeat the statement, people, please check again. Threshold energy, it is the minimum energy which must be possessed by the incoming light radiation for photoelectric effect to happen. Okay, I think from the statement it is very clear. There should be some minimum value of energy which must be possessed by the light, incoming light, or else the photoelectric effect will not happen. You will not be able to see electron coming out. Right? That's fine. Right? Okay. Now, so fine. See, what you have to understand is you have to remember law of conservation of energy. Law of conservation of energy. Right. Now, what it says, obviously, it says that energy can neither be created nor be destroyed, but be transformed from one form to another form. So, what I'm trying to tell you is that during this entire process, right? During this entire process, I have metal surface, light is falling on it, electrons are coming out. This entire process, energy conservation should happen. That means what? You are supplying some energy through in the form of light. Okay. Now, okay. First, we'll try to understand. Right. So there are 3 things involved here. One is the energy you give. Right. This is the incoming energy. Okay. Now, this incoming energy is going to be used in 2 ways. What is the two-way? Obviously, first, it should be more than the threshold energy. Right. Now, okay, fine. We'll come to this next part. Now think about it and tell me, I told you that this threshold energy is different for different metals. Can you tell me why? Threshold energy is different for different metals. Why? Can you come up with a
Sir, their ionization energy is different.
Absolutely true. Right. Obviously, every element will have different ionization energies. Okay, so obviously, if the ionization energy, like the energy you supplied here in the form of the radiation, if it is lesser than the ionization energy, obviously only then the photoelectric will not happen because electron will not be able to come out, right? So I would say this threshold energy, you can actually even write it as ionization energy. Okay, now, or you can write it as threshold energy or ionization energy, or if at all you want another technical term, this can also be called as work function of the metal. Okay, so we have three terms now. Threshold energy is nothing but the ionization energy, or it is also called as work function of the metal. Okay, so what you understand is the incoming energy of the light is going to be used up in two ways. What is the two ways? Obviously, to supply ionization energy for the electron to come out. Okay, now once the electron comes out, what is happening? It is not that it is still, right? It is still moving, correct? So obviously this another part where it is going to get spent is in the kinetic energy of the electrons. Is it not? Hope you understand. The energy of incoming light is going to be used up in two ways. Only those two ways are possible. No other things are possible, right? One is to overcome the ionization energy or work function. Second thing is, once you overcome it, if I still have more energy, what will happen? The electron will start keeping on, whatever electron is coming out of the surface will start moving, right? And anything moves will have some kinetic energy, correct? Right? So this is the incoming thing, and these two are the outgoing things. So if I observe that law of conservation is still obeyed, obviously the incoming and the outgoing thing should be equal. Okay?
Sir,
tell me.
Sir, suppose the energy of the incoming light is equal to the threshold energy, and the electron has been taken out from the atom. So, okay. But it does not possess any kinetic energy because all the energy is spent in overcoming the threshold energy. Okay. So, can the atom attract the electron back again?
Possible, should be possible, because what will happen is, say this is the metal surface, I give the energy, and this is exactly equal to the ionization energy. If that's the case, what will happen is from inside, the electron will come to the surface. That's it, right? But for it to move, obviously the energy has to be greater than the threshold energy, ionization energy. So if it is going to be exactly equal, the it might be that atom might be able to accept it back, right? Now, why? Because electron being there, it is going to become very unstable. Okay, or what will happen is, say the electron is here on the surface, right? Say I don't know whether you know this. There are two bands. One is what is called as VB, valence band. The other one is what is called as conduction band. These are basically energy levels. So an electron will generally be here. The valence electron, the large shell electron will generally be here at the lower level, valence band. If you supply energy, it goes to the conduction band. It doesn't mean that it is out of the atom. No. This is still inside the atom. It goes to the conduction band where it will be able to move this side and this side inside the conductor if it's a metal, right? So what I'm trying to say is, say I have the metal, the electron is here. Say this is the valence band, and say obviously on the surface or near to the surface is what I have the conduction band. So the electron goes here. Okay. So if the electron goes here, what will you understand? When the name itself, you see conduction band, these are the electrons that are responsible for the metal to be a conductor. We know that for anything to be a conductor, I should have some electrons which can move, correct? So if the electron is in valence band, it cannot move. If you little supply some energy, it will go to the conduction band, then it will be able to move. Then the metal will be a good conductor of electricity. Okay, so the electron might be there. So what would have happened is, if the electron is not going to go back into the metal itself, right, it will stay in the conduction band. And now what it would have done is, basically you would have increased the conductivity of the metal, whichever metal you are using. Say it would have been a little insulator before. But if you supply energy exactly equal to ionization energy, you are going to make it a good conductor of electricity. That might be a possibility.
Okay, sir.
Okay, right? Fine. So what I told you is that the incoming energy and how it is used, all of them should be equal, because law of conservation of whatever you give, that's what will come out. Correct. So if I apply law of conservation of energy here, I'll write energy of light incoming is equal to the threshold energy. I'll write as TE, right? Or write it as WF, work function, whatever it is, plus the kinetic energy of electrons. Yes, this is a beautiful equation, very important equation. Okay, energy of the incoming light is used in two ways. One is the threshold energy or the ionization energy or the work function plus the kinetic energy of the electrons. Okay, right? Now, say now I can write a little more detailed equation, right? I know E is equal to h nu, right? I know this formula, Planck's equation, right? So this energy of light, I write it as h nu is equal to work function, right? Now work function, I have a symbol called psi. Okay, work function written by the letter psi. Okay, this is the work function, right? Plus the kinetic energy of electrons. Oh, I'm sorry, the symbol is wrong. I'm so sorry. The other psi should come. Okay, this symbol. Put a circle and draw a line. Okay, so this equation also you can remember. H nu is the incoming light's energy. Phi or psi, whatever you want to call it, that's the work function, plus the K is the kinetic energy. Okay, now I can still more write a detailed equation. H nu. Now for your work function, that is also energy, right? This is also some energy that will have some frequency. I can write that as h nu naught. H nu naught is nothing but psi. Okay, and this nu naught, we know h nu naught is the threshold energy. Okay, this nu naught is the frequency. I'm going to call it as threshold frequency. Okay, so h nu is the energy of light. This is the work function psi. Psi can also be written as h nu again, because that is also energy. Only the frequency will be different, obviously. H is a constant, right? Now this nu naught, which I wrote here, is what is called as threshold frequency, because that is the frequency related to threshold energy.
Sir, could you repeat, sir?
Yeah, sure. So what I'm telling is this entire term h nu naught, basic plus kinetic energy, obviously. This is the entire term, right? This is the entire equation, right? This is the energy of light. This is the kinetic energy of electron. This is my threshold energy, h nu naught, right? The psi, which I wrote here, that is the threshold energy. Okay, now this threshold energy again can be written as some h into nu, right? So I already used a nu here, so I'm using nu naught. That's it, for just to be different, right? And this nu naught is what is called as threshold frequency. Why? Because it is related to threshold energy, right? So I would say threshold frequency is the minimum frequency which must be possessed by the light for photoelectric effect to happen. Is it not exactly similar to the threshold energy definition? Instead of the term energy, you use frequency, because I know energy and frequency are related. How? E is equal to h nu, right? So this nu naught is what is called as threshold frequency, because it is the frequency of threshold energy. Are you able to understand? Is it okay?
Yes, sir.
Okay, everybody understood. And this, I would say, out of all the equation, this equation, if you remember, it is going to be most helpful. H nu is equal to h nu naught, where nu naught is the threshold frequency. This nu is the frequency of light, incoming light, and obviously K is the kinetic energy, right? And one more also detail I can add. I know the formula for kinetic energy, right? So I can rewrite this as h nu is equal to h nu naught plus half mv squared. This can also be this, right? Now, in this case, what you have to understand is here I have to substitute the mass of electron, right? Because we are talking about electrons as kinetic energy here. So mass of electron is what should be substituted here. Okay, but mostly you will not be using this equation. 90% of time you will be using only this equation, right? H nu is equal to h nu naught plus kinetic energy of electron. Only difference is the kinetic energy of electron. I can write it as half into mv squared. All you have to understand is mass of electron should be used. That's it. Okay. Can I get S from everybody if they understood photoelectric effect, the equations, the concept, everything related to photoelectric effect is over? Can I get S from everybody?
Sir, could you give a definition for photoelectric effect?
Definition for photo? Yeah, sure, I can give you. Please take it down. Okay, everybody can take down photoelectric effect definition. It is the phenomenon of emission of electron. It is the phenomenon of emission of electron from a metal surface. It is the phenomenon of emission of electron from a metal surface which is illuminated, by a light of suitable frequency. By a light of suitable frequency.
So can you run through the definition once again?
Yeah, sure. I'll tell you again. So it is the phenomenon of emission of electrons from a metal surface which is illuminated by a light of suitable frequency. Okay, so when light of suitable frequency falls or illuminates the metal surface, electrons are emitted. That's what is given in the statement.
Sure.
Right? Okay, everybody's okay?
Yes.
Right, okay. Yeah, can I get a S from everybody? If they understood everything relating to this photoelectric effect, the equations, the concept, whatever, everything we saw, is everybody okay, guys? Can I get a S from everybody?
Yes, sir.
Okay, 1,
Sir.
2. Chat also I can put if you are not able to unmute yourself. Okay, something in the chat. Sir, can you repeat from kinetic energy? Okay. Okay, I think I'll start from here. Where is it? Okay, so what I have to understand is, Raghav, so we have the energy of the incoming light. Okay, this incoming light's energy, how it is used is the question. Okay, now it is going to be used up in two ways. What I told you, first thing would be obviously to provide the ionization energy because the electron has to first come out. Okay, so that energy is spent. That is my ionization energy. And second way it is going to be spent is now obviously if the electron is going to come out and it starts moving, right? Obviously anything which moves will have some kinetic energy. So two ways in which the light will be energy of the light will be used. One will be to overcome threshold energy and second would be in terms of kinetic energy of electron. Okay, so obviously if I apply law of energy of conservation, so the incoming light, or the incoming energy should be equal to the outgoing energy, or in the sense that whatever, say, energy you give should be equal to the energy spent. Is it not? It cannot be lesser, it should not be higher. That's the point. So that's why we write the energy of the incoming radiation, light, is equal to the threshold energy plus the kinetic energy, because this is the only two ways in which the light can be used. The energy of the light can be used. Right? Now this, I can write it now of equation. I know E is equal to HQ. I'm writing it. I'm going to give a symbol for threshold energy or work function that is called psi. Okay, and plus the kinetic energy of electron. Okay, now this psi, which we write here, psi, again, that's an energy value, right? This is also energy value that I'm going to write it as H nu naught. So this psi is what is called a, okay, this psi is what is called as threshold energy. H is a constant. So this is what is called as threshold frequency, right? This nu naught, we wrote it here. Threshold energy is equal to H into nu naught. This nu naught is what is called as threshold frequency. Now, how can I rewrite the equation then in terms of H nu naught? H nu is equal to H nu naught plus kinetic energy of electron. This total H nu naught is my threshold energy total. In that, nu naught is my threshold frequency. Okay. And at last, this kinetic energy, I know the formula Ke is equal to half mv squared that I wrote here, right? But all you have to understand is we're talking about electrons which are coming out. So I have to put electrons' mass value there in terms of mass in half mv squared, where m is the mass. In that case, you have to substitute mass as mass of electron. Okay. Raghav, is it okay now? Understood? Okay, good. Yeah, so I got three responses now. 2 people said yes. Raghav asked this question. He answered. Guys, everybody's okay. Come on, I know 12 people are there. Can everybody respond? Navya, Hamsini.
Yes, sir. Understood.
Okay, Raghav, I think now just now he asked. Tanishk. So many people I'm saying. So
yes,
it is
sir.
just it is just for my satisfaction, people. Like, because if you are here, I mean, if you are physically present, I'll understand whether you understood or not, looking at your face. But this will be very difficult. That's why I keep on asking you. Anyways, if everybody is okay, I'm okay. Yeah. So good. Right. Anyways, good. I hope everybody is following. Right. Fine. So maybe we'll do some problems on what is the time push. Oh, what I forgot to give you breaks. I'm so sorry. Guys, we'll take a break. For time is now 7:24. We'll meet by 7:35. Okay, we have my break of almost 11 minutes. Okay, we have 7:35 we'll meet, and the class will go on till 8:10. Okay, the class will go on till 8:10. The break for you, because it's supposed to be a 2 hours class. Okay, so we'll take a break now. Okay, for 10 minutes, and we'll be back. Okay, so like, you don't have to go out of the meeting. Don't leave the meeting. Just unmute yourself. I mean, you're already unmute. Just keep your phone wherever it is and you can go. I'm also not going to unmute. I'm not going to come out. I'm just going to unmute and stop my video. Okay. So now your time starts now. You can go. Right. And I'll be back in 10 minutes. I hope everybody's back. Are you guys back? Is everybody there?
Yes, sir.
Yes, sir.
Great. Right. So let us start with the problem. Okay. Yeah, maybe we'll start with some easy problem. Fine, take down. The threshold frequency for a metal. The threshold frequency for a metal is 7 into, write the value, is 7 into 10 to the power 14 per second, or it also can be hertz, right? Okay. So the threshold frequency for a metal is 7 into 10 to the power 14 per second. Okay, right. A radiation of frequency, 1 into 10 to the power 15 per second. A radiation of frequency 1 into 10 to the power 15 per second hits the metal. Okay. Now the question is, find the kinetic energy of the emitted electrons. Find the kinetic energy of the emitted electrons. Okay, I'll repeat the question, people. The threshold frequency of a metal or for a metal is 7 into 10 to the power 14 per second. A radiation of frequency 1 into 10 to the power 15 second hits the metal. The question is, find the kinetic energy of the emitted electron. Right? So obviously this question is from photoelectric effect. You can do it. I'll give you a minute, maybe 2-3 minutes. Solve it and tell me. Okay, I hope understand what all is given here. This 7 into 10 to the power 14 is what is my nu naught, that is my threshold frequency. And this is the incoming. Say they said the radiation of frequency of this much hits the metal. So this would be nu. Okay, so you can understand from this, or you can understand from this equation. H nu is equal to H nu naught plus kinetic energy. Right? So nu is given, nu naught is given, H value we know already. Right? Find the kinetic energy. Yeah, please tell me.
Sir, is it 18.18 into 10 to the power minus 30?
No. You're telling 80.
No, sir. 18.
No, then also the answer is not matching. No. Right? All I have to find is this kinetic energy value. That's all I have to find. Right? So if I have to find, I can rewrite the equation like this: kinetic energy of electron. I can rewrite it as H into, one second, H into nu minus nu naught. Right? So how can I write it? Like from this equation, I'll get what? Ke is equal to H nu minus H nu naught. You can take H common out. So it will be H into nu minus nu naught. Yeah, tell me, someone is telling something?
So 19.8 into 10 to the power 20.
19.8 into 10 to the power 20. Yeah, I think it's correct. So basically what you will be getting approximately.
Yes, sir, it's 19.8 only, sir. Sorry.
Yeah, approximately it would be 2 into 10 to the power minus 19 joules, approximately. 19.8 becomes 20 if you keep. And 10 power minus 18 becomes 10 power minus 19. So it will become 2 into 10 to the power minus 19 joules. That would have been the answer to this question. Approximately, obviously. 2 is approximate. Right? Okay, very, very simple. Right? Hope you understood what we did here from this equation. Right? We just have to find kinetic energy. So that would be H nu minus H nu naught. I took H common. It will be H into nu minus nu naught. So this is basically 6.6 into 10 to the power minus 34 into nu value is 10 to the power 15 minus 7 into 10 to the power 14. And if you're wondering, you cannot directly do this, people. You cannot, because 10 power 15, this is 10 to the power minus 14. If you're wondering how the mathematics works, this is how it works. So I can write this as h, that is 6.10 minus 34. Now I have to make sure that both of these are either 10 to the power minus 14 or 10 to the power minus 15. Only then you will be able to subtract them, or you will not be able to directly subtract them, right? So I can rewrite this as 0.7 into 10 to the power 15. Yes, I can do that, right? I write 7 as 0.7.
Sir, or else you can take 10 to the power 14 common.
That also is fine, right? If you take that is also fine, obviously. If you take 10 to the power minus 14 common, I'll get 10 and 7. That is also okay. Either way, right? So now you can take 10 to the power minus 15 common from this, right? So you write 6.6 into 10 to the power minus 34 into 10 to the power 15, which is common. Now what will be left? 1 minus 0.7, which will be basically 1 minus 0.7 will be 0.3. Now if you do that way, what he told, you'll get 3 into 10 to the power 15. That's what you'll be 14. That's what you'll be getting. Anyways, so the end answer, if you do all the calculations, you will be getting the answer as 2 into 10 to the power minus 19 joules, approximately, obviously. Okay, easy question, right? I hope everybody could solve. And guys, I know that you're able to get so quickly the answers even for tough calculation because you're using calculators, right? For this class, it's okay. I'm not telling anything, even though I know, but obviously you will not have this luxury of doing this in your exams, right? Because in your exams, no calculators are allowed, right? So try to calculate only with your hand, right? Because now you might have the leverage, but when you go to the examination hall or when you go for any school exam, obviously they'll not be allowing you for using calculators. Okay, fine. Anyways, we'll do one more question like this. Take down. Okay, this question is a little interesting. Okay, take down. If a light, or right like this, if a photon of wavelength, we know what are photons, people? We just know, right? Sorry, what are photons?
Particles that
carry energy in light.
Best way to put it is the particles which make up light. Basically, light is made up of photons. How atoms, or all matter is made up of atoms. I would say light is made up of photons. It's like that. Okay, so what are photons?
Yes.
Photons are the particles which make up light. Okay, all right. Anyways, so the question is, if the photon of wavelength 150 picometers, okay, photon of wavelength 150 picometers, PM is picometers, strikes an atom, and an electron is ejected, with a velocity of, 1.5 into 10 to the power 7 meter per second. Okay, an electron is ejected out with a velocity of 1.5 into 10 to the power 7 meter per second. Okay, actually, it's not, this thing is not end. Comma is there after 1.5 into 10 to the power 7 meter per second. Put a comma. Then find the binding energy. Of the metal. Okay, I'll repeat the question, people. If a photon of wavelength 150 picometers strikes an atom, or again, right, strikes a metal, right? An electron is ejected out with a velocity of 1.5 10 to the power meter per second, 10 to the power 7 meter per second, right? Then find its binding energy. We have to find the binding energy of the metal. Okay, what are they trying to say? Binding energy. What are they asking here, people? What is binding energy?
Threshold energy.
Exactly. They're asking about, see, that the different names can be used. It's threshold energy, work function, or it can be binding energy.
Sir, but then binding energy is different, right?
No. There are the what do they tell by binding energy is, say I have an electron, I have a nucleus, right? So there will be some attractive force between them.
Yes, sir.
Right, energy between them. That is what they call as binding energy. Okay, binding between electron and nucleus. Yeah, please tell me.
Sir, they should mention the either velocity of the photon, right?
Yeah, they have mentioned, right? The electron is coming out with the velocity
No,
of...
sir, the velocity of photon.
Oh, incoming light.
Yes, sir.
Why do you need velocity of that?
Actually, we know the velocity of light, no, sir.
No. See, velocity of light, velocity of light is 3 into 10 to the power 8 is in vacuum. Right? Only if I have vacuum, I have the speed. So if I don't know what is the medium, I don't know what is the speed, because different medium has different speeds. Right?
Sir, this was because to calculate the frequency.
Yeah, exactly. Correct. Absolutely. So you know that it is, E has two formulas, right? E is equal to h nu. You can use the normal, which this is what you have been using till now, or we have E is equal to hc by lambda. So this, yeah, you have to use till it ends about later. No doubt about this. Okay. For this C value, hc A is equal to hc by lambda, right? You know the C value. C value is 10 to the power 8. Okay. So this is the value which you have to use for finding the energy of the incoming light, not this one, because frequency is not given, but lambda is given, wavelength is given.
Sir, picometer is 10 to the power minus 15.
Picometer is 1 picometer
minus 12,
is minus 12, exactly.
Oh, sorry, yeah, 12. Minus 12. Okay.
Yeah. Right. And people, see, look at this equation now. I have energy of light. Okay, I write it as hc by lambda. This is for the light or photon or whatever it is equal to h nu naught. I know the threshold frequency is given. No, it's over. That's what you need to find. Basically, this entire term, okay, we'll come to that, plus the kinetic energy. Okay, now in this question, what they're asking you is this entire term. Okay, this is my binding energy. H nu naught is my binding energy. Okay, now so the same question I can little modify, ask you to find what is the threshold frequency. The question can also be like that. And that might be a different question. The same way, everything is same. But instead of asking you to find the whole term, I can ask you to find only the threshold frequency. That can also be the case. And one more thing, what you have to understand here, this is okay, hc by lambda. This is okay. This entire term only we have need to find. This kinetic energy is, what is the formula? Half mv squared. Right? Now we know the velocity of the ejected electron. This is the velocity of electron that is coming out. Right? So m value, what will you substitute? I told you that you have to substitute mass of electron. Anybody remembers what is the mass of electron value? Mass of electron is
6.1 into...
I think it's 9.1 in 10 to the power minus 31 kgs. Let me confirm that. Guys, all these values you have to remember. Okay, do not forget. See, like it's been so long since I used it, so I forgot. You are in touch with this, right? So you should be able to remember. So what is the question number?
Sir, it is 9.1 into 10 to the power minus 30.
31 only. This value is correct?
Yes.
Okay, absolutely. Then great. Then go on. Okay, so half mv squared you have to calculate. Then this you have to calculate. Then you have to find this entire term, h nu naught. Right? I mean, this is the threshold energy. This is what is asked in the question. Oh. No, guys, this is mass of proton. What I wrote here, I'm so sorry. This value is not the correct answer. This value, what we wrote, is for mass of proton, 9.1 into the power minus 31 kgs. And Oh, no. What are we doing here? One second, guys. 1 second. Just give me a minute. Which question are we solving now? Okay, that's 11. Okay, then what you wrote is correct. Absolutely. I'm so sorry, guys. So sorry to confuse
It
you.
is
This
correct
value is
only.
correct.
Yeah,
Yes,
okay.
yes. Correct. Yeah. 9.1 into 10 to the power minus 13 kg is correct. Again, it involves a lot of calculation, I understand. But take your time, do in your hands, and tell me whether you're getting the answer or not.
Sir, is it 13.19 into 10 to the power minus 12?
13.19 into 10 to the power minus 12? No. I think 13 point something I feel is okay, but check your 10 to the powers. Like the answer is not exactly right, but it's a little close to it. But 10 to the power, what you said is wrong.
Sir,
Yeah.
is it 12.25 into 10 to the power minus 16?
Yeah, correct. Yes.
Sir, actually, they didn't mention whether energy should be in joules or electron volts.
Yeah. Like obviously the H value itself will be different if it is going to be in electron volts. Right? The energy, like we write 6.6 into a minus this thing, right? That H value will be different for electron volts. They will not ask in electron volts.
So now if I convert this answer into electron volts, will it be wrong?
If you, if I have to give you the exact term, 1 electron volt is, I think, 4.1 joules, I guess. Yeah, you can convert this using this, whatever equation. But again, not required. You will not, they'll not be asking you in electron volts.
Fine, sir.
Yeah. Electron volts, like they'll be asking you only for in the case of and the Bohr's theory, like the K value which you use, that it might come, not here or not. Okay, so yeah, the exact answer would be 1.22 into 10 to the power minus 50. Yeah, what you said was 12 point something to the minus 16. That is also correct. The 10 power will be different. Okay, and obviously the answer would be in terms of joules. Okay, so very simple. This equation, if you remember, this is the energy of the light, hc by lambda. The threshold energy is what we have to find, h nu naught, plus kinetic energy, and this thing has to be calculated. So hc by lambda will be 6.6 and then power minus 34 into 3 into 10 to the power 8 divided by lambda value is 150 picometers, so 150 into 10 to the power 12 meters. If you don't put this, guys, the entire answer is wrong, right? 10 to the minus 12 you have to put, because you have to substitute every value here only in terms of SI units. Okay, picometer is not the SI unit, meter is the SI unit, right? Is equal to threshold frequency, will keep it, threshold energy will keep it as T, that's what you need to calculate, plus half into M, that is 9.1. I'm sorry. Right, 9.1 into 1 second, 10 to the minus 31 kgs into V, velocity is 10 to the power 1.5 into 10 to the power 7 square. So big calculation, I totally understand. But these kind of questions only.
Sir, I have a doubt, sir.
Yeah, tell me, yes.
Sir, this is the energy, right?
Yeah, threshold energy.
Yes. Left hand side. Sir.
This one, right? This one is the energy, yes.
Sir, but left hand side should be h into lambda, right?
H into lambda. Why h into lambda? Hc by lambda is the formula for energy.
No, sir. Like the formula is h lambda equals h lambda no. Sorry, h
nu. Okay,
nu.
Okay. Telling
Yes,
h nu into h plus.
Sorry, h nu. Yeah, yes, sir.
Correct. But
so why are we writing energy?
Oh, why are you writing in terms of this? Because lambda is given to you, not frequency. If frequency is given to you, you would have calculated with this equation. But if lambda is given to you, you have to calculate only with this equation. Or you
Sir,
know,
but frequency is not equal to hc by lambda, right?
No, frequency is not equal to hc by lambda. H nu is equal to hc by lambda. Or I can write frequency nu is equal to c by lambda. This I can write. Understood?
Yes, sir.
Okay, frequency is equal to velocity divided by wavelength. That is what we're substituting here. And in terms of nu, you write c by lambda. That's it.
Yes, sir. Understood.
Right. So yeah, if you do all these calculations, people, like if you do all these big calculations, you will be getting the answer as 1.22 into 10 to the power minus 15 joules. And this kind of question, if it comes, it will definitely come in 3 to 5 marks, because it, like, even though the formula is very simple, but it takes a lot of calculation.
Sir?
Yeah.
Sir, actually, the like the answers are varying. If we take what is that? Sir, I forgot the name. Like Planck's constant. Planck's constant value. If we take it as 6.6, answer is coming different. If we take it as 6.62, it is coming different. If we take it as 6.26.
634. Yeah, I understand. That definitely will be different. Yeah. Don't worry.
So now if we go with usual method like 6.6, answer is coming 12.175 into 10 power minus 16.
Okay, but what you have to generally use is you use the 6.62 at least. Like you use at least 2 decimals. 626 should be the ideal case. But instead of using 6.6 in your school exam, you use 6.62.
Okay. So not 6.6.
Yeah, you keep it as now you keep it as 6.6, no problem for our class, whatever we do. But in the exams, whenever you calculate, you use the 6.62. If you use the 6.626, amazing. Like it will be the best one. But if not, you can at least use 6.62. Okay. Right. Fine. So what is the time we have? Okay, 10 more minutes. What should I do? Maybe we'll do one more problem. I don't want to start any new topic. Right. We'll do one more problem actually. Okay, you want to solve some tough question. Is everybody up for it? You, as an MD, good with graphs in physics and all. Okay. Anyways, let me give you. Let me see if you can try. It's not about the calculation part, but yeah. Anyways, so this graph is given to you. Okay, the graph is between frequency on the y-axis and kinetic energy divided by h in the y-axis. Okay, and there is this point A. From this point, I'm going to get a straight line. Okay, and this is my origin. Origin is O. Okay, Now they have given, this is y-axis Ke by h, and in the x-axis I have frequency, right? So they have given OA as 5 into 10 to the power 14 per second. Okay, OA is basically 5 into 10 to the power 14 per second. Right now the question is, what is the work function? It's a very simple, it looks very complicated, but it's very simple, people, right? So you think and tell me.
So is this the frequency of the incoming light?
So you look at the graph. If you look at the graph, you'll understand what is that it is given. Obviously, when I tell you it is not now the incoming frequency of the incoming light, you know what it is. But think about it. How is it like that? That's the point. Yes, anybody can come up. So this, I'm telling you, this is the threshold frequency, mu naught. Can someone explain me how? From the graph, I'm telling you that this is mu naught. How can you tell me? Looking at the graph, can somebody explain? Think about it. I'll give you a minute. Let me see, anybody can come. Any guesses? Anybody can come with any kind of answers. Doesn't matter if it's right or wrong. Whatever you think, you can tell me.
Sir, threshold energy by Planck's constant will give us threshold frequency, right?
Threshold frequency by Planck's constant is threshold frequency. Okay, fine. Yeah. Nobody is able to get it from the graph. How this is the OA, this whatever this here is my threshold frequency.
Sir, is it just Planck's constant into OA?
No, this is the frequency value. This is some frequency. The frequency is keeping on increasing. And you have the graph starting at this point, and they're telling that OA is this this much. And I am telling you from the graph, you need to understand that this is threshold frequency. I'm telling you this is threshold frequency. I'm asking you how. How did I say this is what I'm asking? Okay, answer this question. Till this point, okay, you are keeping on increasing the frequency. And till this point, what is the value of this? Or forget about this h. What is the value of kinetic energy till this point? Till this point, what is the value of kinetic energy? From the graph, what you can tell?
0.
0, right? Like this so you can see this is the y-axis, right? Still it is 0. The kinetic energy is still 0. But once you cross after this frequency, you increase the frequency, then only kinetic energy value is coming. Is it not understood now? Obviously, if I have just energy equal to the threshold energy of light is equal to the threshold energy, obviously that is what is happening till this point. Only the time when, or I write it like this, when nu is equal to nu naught, that is what is still here. That is exactly at this point, this whatever they are telling you. Now, once nu becomes greater than nu naught, obviously kinetic energy value comes, because only then electron will come out. Till this point, electron will be on the surface. right? Now, once you little bit increase the frequency, now the electrons are there in the surface will move, and obviously that is where the kinetic energy is coming from. Is it not, people? That is exactly what is happening here. Till you keep on increasing the frequency, right? Nothing is happening. The kinetic energy is not coming because electron is not coming out. But once you reach the A point, the kinetic energy is coming. That means what? This is the point where the photoelectric effect starts. And that there should be some minimum frequency. Obviously, this OA, that is how I say that this is my threshold frequency. Everybody understood how this is threshold frequency, guys? Is it okay? Yes? No?
Yes, sir.
Okay, I think I'll repeat again. So what you have to understand is, people say I start with 0 frequency from this point, 0 frequency, 0 kinetic energy.
Can you draw it separately once again?
Yeah, sure. What I'm telling is, this is frequency in the y-axis, and this is kinetic energy. Forget about the kinetic energy by h. This is kinetic energy. Okay. So what I'm telling is, say they start with 0 frequency. Obviously, the 0 frequency, no light is there. Right? So obviously 0 kinetic energy. Say now this is 1, this is 2, this is 3, this is 4, like that I'm keeping on going, right? Say 1, 0 kinetic energy, 2, 0 kinetic energy, 3, 0 kinetic energy. But when I reach 4, kinetic energy is increasing, right? After 4, if I just keep on increasing the frequency value, kinetic energy also is keeping on increasing. Okay, obviously now what do you understand? Till 4, till this, I would say exactly at this point, the incoming frequency of the light is exactly equal to the threshold frequency. Once you make the frequency little go higher, say you go to 5, then you see that the kinetic energy is happening. Why? Because for kinetic energy to come, or for the electron to move, the nu should be greater than nu naught, right? So till this point, they were equal. And before this point, the energy of light or threshold frequency is lesser than what is required. That is the threshold frequency. Now, once you reach, then you increase. After that, then only the kinetic energy value is coming. Till then, it is 0. Obviously, what do you mean by that? This is the y-axis. And a y-axis, what do I have? Only the frequency. So obviously, this point, say this is OA, this point is nothing but the threshold frequency. Because after that, only after that, if you still increase the frequency value, only then you are seeing the kinetic energy increasing. Till then, it is 0.
Sir? Sir, then is psi equal to h into 5 into 10 to the power 14? This minus the kinetic energy.
Not required. They're just asking you what is the threshold what is the work function? What is the work function formula? H into nu naught. Nu naught is already known from the graph that is given to you. OA 5 into the power 14. So just multiply this with h. That's it. That's the answer to this question.
Sir?
Yeah.
Sir, instead of frequency and kinetic energy graph, if it was for the energy of light and kinetic energy graph, then OA will be the threshold energy.
We'll see that. So what I'm telling, energy of light versus kinetic energy, correct?
Yes, sir.
Okay. Yeah, that kind also will do. Right. Say now, the same graph only you'll get. Say you start with 0 energy of light, obviously no photoelectric effect. Till some point, the energy of light will be equal to the threshold energy. I write it as ET. That is this point. Okay. This is kinetic energy here, and this is the energy of light here. Okay. So till this point, I say that the energy of light is equal to the threshold frequency. That means the electron is on the surface. Now, little more you do. Now, once the energy of light becomes greater than the threshold energy, now you see kinetic energy values increasing. So this keeps on increasing, this keeps on increasing. Now, this is my phi, right? Yes, the same graph, this is my phi. Now, this is equal to h nu naught. Now, what you're asking is, can I find it nu naught? Absolutely, because I know this value. H is a constant. I can find this value. Yes?
Sir?
Yeah.
Sir, I have a doubt from the previous questions.
Yeah, tell me.
Sir, in the previous graph, sir.
Here. Okay.
Yes, sir. So over here, when so we can write like h into nu, that is the frequency of light incoming, is equal to phi plus kinetic energy.
Absolutely.
Sorry, psi plus kinetic energy. So if we take the h that side, like if we take it to that side, the frequency of light becomes psi upon h plus kinetic energy upon h.
Basically, you're telling frequency is equal to nu naught. I mean, I have basically nu naught plus Ke by H, right?
Yes, sir. Nu naught plus Ke by H. So
Right.
if Ke is 0, suppose at the initial point, if K is 0, then it's given that OA is 5 into 10 to the power 14.
Absolutely. Yeah, this is a very good way of approaching. Yeah, I understood what you're trying to say. Thank you. So the thing is, yeah, tell me. You complete it. Okay.
Sir, so the frequency of incoming light becomes 5 into 10 to the power 14. Correct. So we can equate it. So H into the frequency equals
threshold frequency.
Yeah. H into threshold frequency plus kinetic energy.
Absolutely. See, this is a mathematical way of doing it. Okay, what you're telling here, this is the mathematical way of doing it, and this works, right? But here, what I did is a logical way. Now, this also works very good. See, you understand? If I write like this, H nu is equal to H nu naught plus kinetic energy. Now, what I do is I divide the entire equation by H. Okay. Now, what will happen if I divide the entire equation by H? Now, nu is equal to nu naught plus Ke by H. Right now, you see, if you look at the graph now, what is there in the y-axis? Y-axis I have nu, and in the x-axis I have Ke by H. Right. So this equation exactly tells me that this is of the form y is equal to mx plus c. Okay, where c is the K by H. Right. M, we don't know. Like, okay, this x is what is my nu naught. Oh, I'm sorry, guys. I'm totally messing it up. Like, this should be the other way. I'm so sorry.
Sir, so is the answer same as 5 into 10 to the power 14?
No, it should be H into 5 into the power 14. That is the threshold frequency.
Yes, sir. Yes, sir.
Correct. Right. So anyways, so now I write it like this. Right. So y is equal to c plus mx. If I write, now this x-axis only I have this Ke by H. Okay, x-axis only I have Ke by H. Slope in this case is 1, right? Because there's nothing here. There is no coefficient. So slope is 1. Now you see this C is what is my intercept. Well, hope you all know straight lines. What is the equation? Y is equal to mx plus C. Now this C is what is my intercept. Now this C will come when y is equal to 0. Anyways, so this is what is my intercept. So I can easily tell this is my C value, right? Whatever the value which I have here is my C value. And according to the straight line equation, what I'm getting, that C is nothing but the threshold frequency.
Sir, but according to this, the psi is getting a different value, sir. It's H nu naught minus K by H.
H nu naught minus, yeah, obviously, correct. H nu naught. I don't understand what you're telling. What? Nu naught is?
Sir, after equating, which I told before earlier, so the frequency that is 5 into 10 to the power 14, that is the so H into, sir, so H into 5 into 10 to the power 14 is H nu naught plus K.
No. This nu naught is what is my 5 into 10 to the power 14. Okay. So this nu, we don't know. We actually don't know these values. Like in the graph, have they given you any values here? No, right?
Sir, we calculated the new value now, sir.
We didn't calculate. We just said that this is nu naught. OA is nothing but nu naught. And we calculated threshold frequency as H nu naught. That's it. That's all we did. Did you understand?
The point H is 0, sir. I mean, sorry, K by H is 0. So this is 5 into 10 to the power 14.
Okay. So you're telling that if in this Ke by H is equal to 0, this entire term is 0. Now
yes,
what will happen?
So,
this will become equal to nu naught. Nu is equal to nu naught. Correct. When nu is equal to nu naught, obviously there is no kinetic energy. Obviously, that is exactly what I'm telling. If you go by mathematics or you go by logic, if it is going to become equal, there is no kinetic energy because no electron will come out. Once this becomes greater, then that how much ever it is greater, that is what is in the form of Ke by H. That's what I would understand. Yes?
Sir, no, what I was asking was, after this point, we get nu as 5 into 10 to the power 14.
Okay.
Sir, and then if we equate in the previous equation, H nu equals H nu naught plus K.
Okay, this one, okay.
Sir, then h like h nu equal like h into 10 to 5 into 10 to the power 14 equals h nu naught plus ke. So h nu naught is the psi.
Why are you putting this value as 5 and 10 to the power 14? I don't know why are you putting this value. This nu naught is what is.
We got that value below, right?
No. See, this if you just see, obviously here, this nu naught is also a frequency. That is just one of the frequencies we keep on increasing, right? So you can, if you include that nu is equal to nu naught, obviously their kinetic energy is 0, right? If you want Ke by H term, the kinetic energy term to be here, obviously this and this are not equal. That is what you need to understand. Only when this is equal, kinetic energy is not there, 0. Like after equating this, you cannot go back here. That's what I'm telling. Because if you want kinetic energy, the nu naught should be greater than nu, not equal to. Do you understand my point?
Yes, sir.
Okay, good. Right.
Sir?
Yeah, tell me.
Sir, can you once draw the graph?
Sure. So you want the frequency graph and energy
frequency graph? And kinetic energy by H.
Okay.
Yes, okay. Sir. Now let us multiply H on both the axes.
Okay.
So you will get H nu and here kinetic energy. Yes, sir. Yeah. So can you write OA?
Yeah, OA.
Yes, sir. So here OA should be the threshold energy, right?
Absolutely. OA should be H nu naught. That is the threshold frequency, threshold energy.
Yes, sir. But then how is the answer H into 5 into 10 power minus into 14? It should be only 5 into 10 power 14, right?
Okay. In this case, you multiplied it. So whatever the value you will get, it will be the energy value. Basically, I can even write it as energy. Correct? Yes, so what will you be getting here is energy again. This is again energy. But if this was frequency, what you will be getting is only frequency. Then if you want to get energy, obviously this has to be multiplied by H. Only then you'll get the energy value. Correct?
Okay, sir. Got it.
Right?
Yes, sir.
Okay. Any other questions anybody has? Okay, fine then. I think we exceeded the time by 10 minutes. Okay, I think we'll stop here, guys. Right? Fine. Thank you so much. We'll meet again tomorrow.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you. Thank you.